So let's try to do some of these problems on a ramp. Let's say we have that penguin on an icy slope, but it's not frictionless. The angle of the slope is 11 degrees, and the coefficient of static friction is 0.2. Does the penguin stay stuck on the slope, or is this penguin going to slide? We don't have the mass of the penguin, but we're not going to need it. We are going to do the standard force problem strategy. We're going to draw a picture. We're going to have a free body diagram and a type agent object table. We're going to write down all our known values. We're going to find the x and y components of any forces that aren't on the x and y axes. We're going to write down forces, either equations from the forces, either from the free body diagram or Newton's second law. We're going to solve equations algebraically, plug in our known values with units, and then get the final value with units. So let's do this for the case of our penguin. So here is our penguin. It's on an icy slope. We know that this angle is our 11 degrees. I'm just going to call that theta. I'm going to attempt to draw a little penguin. That's good enough for me. And we need to draw a coordinate system as well. And it's particularly important this time because the coordinate system is not going to be our just normal x goes to the horizontal and y goes vertical, because we have a surface that is inclined. And since the surface is inclined, the motion, if there's any motion, is going to be along that surface. And we want to align our axes along that direction of acceleration, if there's any acceleration. And so we're going to have our x-axis point along that direction, and our y-axis is going to be perpendicular to our x-axis. This is going to greatly simplify any equations that we come up with. Now, just to think about what our free body diagram is going to look like, let's go ahead and sketch the forces on this picture. So the forces that we're going to have are weight or gravity pointing straight down. This isn't a real free body diagram we're drawing right now. This is just sketching it out to see what directions the force go. We're going to have friction, and friction is going to be exactly backwards in the x direction. And we're sort of assuming it's going to be static friction. We're going to see if static friction could possibly be large enough to keep the penguin still. And then we're going to have a normal force. And the normal force is perpendicular from the surface. That's what normal means. And so the normal is going to be in the y direction, because that's perpendicular to the x direction. And x is along the side of the hill. So these are our three forces. All we have to do now is convey those into the free body diagram. Our free body diagram is oriented along these axes. So what you could do basically is think about rotating this, and that is the orientation that we're going to draw these in. Forget the side of the hill entirely now. This is the x-axis, this is the y-axis, and we're just going to be drawing these arrows relative to those axes. Okay, so our weight is going to be going down in this general direction. And by the way, if you remember from our other video, this is our angle theta right there. So it's going to be a small angle. So we're going to be going mostly down and a little to the right. So I will be going, just pick a number, maybe 3 tick marks down and 1 over. So that will be weight. We'll add that to our chart. We have weight, the agent is Earth, and the object is penguin. Okay. We don't yet know if static friction is going to be large enough to counteract weight. That's the point of this problem. So for our purposes, we will just, for the free body diagram, assume that it's the same magnitude. You could assume that it's smaller, but I didn't leave enough tick marks to assume that it's smaller. That's fine. And then finally with the normal force. Now, the penguin, whether it's moving or not, would only be moving in the x direction, not in the y direction at all. So there's no motion in the y direction. The normal force has to cancel out with the weight in the y direction, but only in the y direction. So now we have a free body diagram from which we can write down equations. Our first equation is that the normal force has to equal the y component of weight. From our other video, we know that Wy is equal to, here is our angle theta. This is the y part, so this is W cosine theta. And the equation for W is mg, so it's mg cosine theta. So n is equal to mg cosine theta. We know g, we know theta, but we don't know mass. I did not give you that in this problem. So we have worked our y equation as far as we can. Let's look at our x equation. Now, the point of this question is that we don't yet know if the penguin is moving. So there are two possible cases. Either W is greater than Fs max, and this is penguin moves, or W is less than or equal to Fs max, which means, this is only the x component of W, right? Only the horizontal part, which means that the W is going to be exactly equal to the static friction, the x component is. Because if static friction is bigger, then the penguin would be sliding uphill because of the static friction. And that doesn't make sense for friction to make the penguin slide uphill. And in that case, the penguin is stuck. Right. So, what we're going to do is to look at the equation of Wx and Fs, particularly Fs max, and see how they compare. So we're going to have Wx, and then we're going to put a greater than question mark Fs max, and we're going to plug in what we know. Well, again from the other video, we know that Wx is equal to W sine theta. Remember, if we look at this, this is the Wx. It's on the opposite side of the angle, so that's the sine. And W is equal to mg sine theta. So on the left-hand side, we have mg sine theta. And we're trying to find out if that is greater than Fs max. There's an equation for Fs max, and that equation is Fs max is equal to mu s times n. We have mu s, I gave it to you on the page, and we have n over here, we solved for it. So this is equal to mu s mg cosine theta. So we can plug that in to this expression. So now we have mg sine theta, and we're asking if that is greater than mu s mg cosine theta. So look at what we have on both sides here. We have an mg that we can divide. Mg is always positive. Remember when we have the magnitude g here, when we have the letter g, the letter g itself is equal to the 9.80 meters per second squared. And then when we're talking about applying it as a vector in the y direction, that's when we put in the plus or minus. But g itself is just the magnitude. So since these are both positive, we don't flip the inequality. And then we could also even divide by the cosine, right? If we divided both sides by cosine, we could get tangent of theta question mark greater than mu s. So remember what we're trying to find out here. If the left-hand side is greater than the right-hand side, then the penguin is going to move. So let's see. We have tangent of 11 degrees, and we're asking if that is greater than mu s, which was 0.200. So we're just going to calculate the tangent of 11 degrees. And we get 0.194. So we find out in this case that the penguin just barely does not move. So let's say the penguin has a running start. So it never has static friction to begin with. It runs, it jumps, and it's sliding down the hill from the beginning. We have the coefficient of kinetic friction, and we want to know its acceleration as it's sliding down the hill. We still don't have the mass, but I think you'll see now that we don't need it. So we have a very similar setup as before. The picture is going to look almost identical. See if the penguin is better or worse, or the same. The only thing this time is that it's already moving. The one thing I'm going to change is that I'm going to give myself a little more room with the weight. Really, what I should be doing is making the friction smaller, but I didn't plan ahead, so what can you do? We should already know that the y component of the normal force and the y component of the weight should cancel out. And we should have an inkling that the kinetic friction should be smaller than the x component of the weight, because in the previous case, the x component of the static friction was just barely enough to counteract the weight. And kinetic friction is quite a bit smaller. We'll just repeat the TAL chart. Actually, in my class, I don't make you repeat the TAL chart completely if the forces are the same. So we'll just put the new force, so the agent is still the ice, and the object is the penguin. Actually, you know what? I didn't finish the TAL chart over here, did I? So we'll just put the normal force, since we forgot it last time. The agent is the ice, and the object is the penguin. There we go. Okay. Some of the equations are exactly the same as before. So for example, we have normal equals Wy, which we know is mg cosine theta. No need to repeat that in detail. We also know that the x component of weight is not equal to kinetic friction now. So instead of just setting them equal, we need to write down Newton's second law in the x direction. On the left-hand side, we're going to fill in the forces. Everything pointing to the right is going to get a plus sign. Everything pointing to the left is going to get a minus sign. So we have the x component of weight. We subtract kinetic friction. And that is going to be equal to max. We know the x component of weight is mg sine theta. That's just like before. Minus fk is equal to max. And there's an equation for fk. Fk is equal to mu k times n. So we'll plug that in to our equation. So mg sine theta minus mu k n is equal to max. Probably see where we're going with this. N, we can substitute in for what we have over here. So we have mg sine theta minus mu k times mg cosine theta is equal to max. We still don't know the mass, though. If we look through the rest of this equation, we don't know mass. We know g, we know theta, we know mu k, we know g, we know theta, and we're looking for x. So mass is the only thing we don't know, besides ax, which is what we're looking for. But mass appears in every term, so we can divide by mass. And it cancels out. And so the equation we're left with is ax is equal to g sine theta minus mu k cosine theta. And we can plug that in. 9.8 times sine of 11 degrees minus 0.1 cosine 11 degrees. 0.908 meters per second squared. Oh, I did forget a step that I do require, which is plugging in the numbers with units. So I will backfill that. So sine of 11.0 degrees minus 0.100. Oh no! Plan ahead. Cosine of 11 degrees. Close enough. All right. There we go. So that's how we do problems on ramps. One last thing I'll point out. If you remember in two-dimensional kinematics, the equation that we had for the acceleration on a ramp was just ax is equal to plus or minus g sine theta, right? And that's what we have here, except there's an additional term for the friction, right? So if the friction was equal to 0, we'd be left with the g sine theta that we had at that point. Okay.